Thank you. Thanks, Martin. Thank you very much for the invitation. This is a great conference, great community. I'm having a lot of fun. So the good news is that I'm not going to talk about superconductivity, and so you don't have to sit through another one of those talks. So I'll try to tell you about our sort of ongoing efforts, more broadly defined, to generate order by light. This is supposed to be a crystal emerging from a liquid with some chiral structure in it, and it's actually a pretty picture. So this business of optical control of complex materials might be defined as follows. You have a number of stable phases in equilibrium. You have regions of the phase diagram that don't have any particular form of order, or at least not the order you are interested in. You want to shine some light on them or perturb them, and you want to generate a new section, phase which exists only by virtue of the fact that the system is either driven. This phase might be metastable, might only exist whilst the system is being driven, or you can take this as broadly as you want. So a couple of considerations now. Generally, if you take a material, let's say that now this is your equilibrium phase, and you shine light on them, by and large, what's going to happen is that the material gets energized. I have some order, maybe pre-existing in the material, and the response of the material will be going from an ordered state to a disordered state. That's most, unless you think about what you're doing, that's what's broadly what's going to happen. So this, we can think about the idea of having some liquid, you irradiate it with light, and the liquid boils. So you go from a boring state to a more boring state, if you wish. Of course, you can think about, so if you want to induce order by light, one of the things you should imagine is doing is you have a disordered state. You should not drive the excitations of the state necessarily directly. You should think about having an auxiliary excitation that is coupled to what it is that you want to order. You may want to excite, saturate this transition, and this, if you're lucky and if you do things properly, you can order what it is that you wanted to freeze. So this is actually one example of this is the Overhauser effect. There's NMR tricks where you can saturate one transition and order other things. So this is not something that we necessarily have to invent. So what you really want to do is to take this glass of water, shine light on it, and make ice out of it. That's basically the story. Over the past few years, we've actually taken a shine on a number of fluctuating phases of quantum materials, such as fluctuating ferroelectrics, or failed ferroelectrics like strontium titanate, fluctuating ferromagnets. This is a collaboration, so John Curtis is here. Anki Diza led this. This is a sort of a failed ferromagnet to yttrium titanate, where we showed that you could resurrect ferromagnetisms at high temperatures. And then there's this whole business of optically driven superconductivity. And this is not what I will talk about today. I'll tell you about a few other things that have to do with the control of crystal lattices and the structure of materials with light. So this is my sort of introduction. Some wise men said if you want to understand function, you should study structure, and maybe we should say that if you want to control function, you should control structure. This is the ultimate goal. Come again? Anonymous 2025. This is not just... So the way we've been trying to think about this use of auxiliary excitations to drive order in a material is, amongst other things, has been this business of nonlinear phonon excitations, which turned out to be a very rich way to address coherent manipulation of the structure of materials. Basically, you have a material, it has a number of normal modes, some of them have a dipole. You use a light field that is resonant with one of these dipolar modes, and you drive it to very large amplitudes, and you drive the displacements up to many percents of the unit cell, getting really into the nonlinear response regime. And if you think about the physics of the problem, of course, you don't only think about the energy of a single oscillator, which will be, one of these springs, but really you should think of, and the coupling to the laser, but you have anharmonic interactions amongst normal modes which become dominant. So this is actually something that is not unlike a nonlinear optics problem, except that it involves phonons, that there's many and they disperse and they couple. And so these are sums over all mixtures of 3 phonons, 4 phonons, 5 phonons, etc. So we'll think about this in the perturbative, in a perturbative sense, where this quantity is smaller than this, and 5 phonons and 6 phonons, one is smaller than the other. So just to remind you what this thing allows me to do, if you take a very oversimplified description of this nonlinear phonon Hamiltonian, and you decide that in your material there's only 2 modes, one that you drive and one that is a spectator, that the coupling is only a cubic order, so 3 modes, and that the material is centrosymmetric, which means that modes are either even or odd, you end up with just one single term in your energy function, which couples the square of the driven mode with the one or more, in this case, one of these spectator modes. And so the protocol is the following. You have a light field. The light field acts as a force onto a damped harmonic oscillator, which then is driven in quadrature with the force. And so you have this IR active mode that starts fluctuating at very large amplitudes by virtue of the fact that this light field is big. And now, because IR is coupled to Q2 using that Q square Q coupling, you have to write 2 equations of motion. One is the equation of motion of the driven mode, which is this guy, which then will generate a force on a second mode, Q2, which normally would not be excited by the light. And the force is proportional to the square of the red coordinate, which is the directly driven one. So we'll have a direction, and so we'll apply a displacive force onto the spectator mode. This is the equivalent of optical rectification in nonlinear optics. So you shake this mode and you distort, you displace the other modes, which may involve bond angles and various things, and you create a transient crystal structure. As long as the first mode is shaking, there will be a transiently displaced crystal structure that comes from this rectification of the mode. So that's the 0-order nonlinear phonon. It's very limited in the things that you can do, but generally you can take a low symmetry state and make it higher symmetry. But there's a number of things we've been looking at over the years, including melting stripes, changing bond angles in superconductors, switching manganese oxides from insulator to metals, switching ferroelectrics, etc. So there's a number of low-lying fruits that we've been trying to study. So more recently, but this really doesn't help us if we want to take a disordered system and make it ordered, which is at this level of approximation. So let's just think about something else. I gave you 3 assumptions. Let's just relax one of them, that you only have 2 modes. Let's imagine that you have 3 or more modes that participate in this nonlinear phonon Hamiltonian. We're used to this in nonlinear optics. We're used to taking a red beam and an orange beam and making a green beam. So we're used to 3-mode couplings at the lowest order nonlinear optics. And so if you write the equations of motion, again at the 3-phonon mixing level, in a centrosymmetric material, what you'll have is 2 lasers that drive 2 phonons, phonon number 1, Q1, phonon number 2, Q2. These are both being shaken. And then phonon number 3, Q3 will be displaced as long as Q1 and Q2 are remember, before we only took Q1, we squared it, and we coupled to Q2. Now I multiply Q1 by Q2, and I mix. So I have this trilinear term that displaces Q3 by virtue of the fact that Q1 and Q2 are excited. What's interesting about this is that the force that the combined excitation of Q1 and Q2 applies on Q3 depends both on the amplitude of the driven Q1 and Q2 modes and the cosine of the phase, of the relative phase between the two. So if you're good enough to build two lasers of which you can control the register, the phase register between the two fluctuating modes. You can exert a force on mode Q3 with a direction that is either, you could sort of control the phase of this displacement. One application of this has been work that Ankit did with us. I'll just sort of skim this. I'll sort of show you only one slide about this. Ankit is now at Cornell, running his own group. He took this old problem of piezo-magnetism. Piezo-magnetism is a problem where you have a perfectly compensated antiferromagnetic lattice, and is one where application of strain, either tensile or compressive, unbalances the two sublattices, making a ferrimagnet in either direction. So unlike magnetostriction, this couples strain and magnetism at linear order, so allows me to have positive or negative ferrimagnetism. And so he basically applied three-phonon mixing to drive the equivalent of piezo-magnetism using optical phonons alone, so at constant volume. And he could show that you could generate magnetic order, ferrimagnetic order in either direction at amplitudes that were at least 1,000 times larger than what you can do with piezo-magnetism, because volume-preserving excitations don't crack the crystal. And so he could basically emulate what strain does, but just push it much, and he could do it faster, etc. There's other things you can do, of course. This thing doesn't have to be 0 or pi. You can also use this cosine. So this cosine can also, you could drive two modes in quadrature, and all of a sudden what's going to happen is that the atoms will start rotating in circles. The cation will go right, and the anions will go left, or vice versa. This is actually things that we were inspired by things that people do routinely in optical lattices. They have these artificial gauge fields that are generated by rotating atoms. So this is Tobia Nova, who was a PhD student with me, and he showed that you could couple to magnetic order by driving these ions in circle. James, who's here also, is now at Columbia, showed a variant of this, which is the opening of a topological gap in graphene using circularly polarized light. And although he never says it, when he was doing this experiment, he was exciting at a frequency that was very close to a phonon of the system, presumably moving the AB sublattices this is also a form of Floquet engineering that opens the topological gap in graphene. So this is actually something that has opened up a number of other applications. So now I'm going to get to my own talk today. So this is just by way of introduction. You can do some shaking and manipulate the crystal lattice, and if you can control all these Hamiltonian terms, there's a number of creative things you can do. So this is work done by my student Paul Zhang, who's actually only a second or third year graduate student, but every day he blows me away. And he worked on the problem of chirality. Can you take a achiral crystal and make it chiral, or can you take chiral plus and make it chiral minus? So in principle, this is a very difficult problem. There is not really a phase transition that takes a right hand and makes it a left hand, because you need to break all mirrors and all rototranslations to make a right hand a left hand. And so in principle, if you want to take a right hand, you melt it. This is quartz. You melt it and you make another hand, and then if you're lucky, you'll make the hand the other way. But you can't go between one and the other by a field or by sort of driving the phase. What Paul came up with so he looked at BPO4. This is a piezoelectric, which is what we call an antiferrochiral, has an antiferrochiral unit cell, in the sense that within the unit cell, you have both the right hand and the left hand, and they are perfectly compensated, and so the crystal is completely achiral, just simply because the right hand and the left hand have the same size, if you wish. Okay, so this is BPO4. It's a nonlinear optical crystal that you can buy at Safeways, but nobody had really sort of looked at it in this light. There is one specific phonon, which is of B symmetry, that now I'm looking from the top, and I have my right hand and my left hand. One is red, the other one is The other one is blue. This is the antiferrochiral state. This phonon is not displaced. Right hand and left hand are the same. Of course, if you displace QB in the negative direction, you can make left hand bigger, or if you displace QB in the positive direction, you can make right hand bigger. So you don't really have to break these symmetries. You can make a achiral crystal chiral. What's great about this is that if you look at the nonlinear phononic problem, this is my QB, this is a force, this is my QB phonon that I want to displace. And this can be displaced by driving, by shaking, either one of two doubly degenerate modes of E symmetry. So, and you can see there's a minus sign. If you pump this phonon, which is some phonon polarized, say, along this direction, you will have a force on QB, you will displace QB in the positive direction. If you pump this other phonon, you will displace QB in the negative direction. So you'll take the red hand, either make it bigger or make it smaller. So this is, there you go. This is an insulator. You have a very sharp, doubly degenerate mode, with, either measuring along the A, pumping along the A or along the B axis. You can do DFT calculations and convince yourself, you can solve the equations of motion, and you can convince yourself that if you pump QA, you will get chirality in either direction for reasonable fields. You can probe chirality using, where is this? By looking at, this is again calculations of the equations of motion. You can have a second probe pulse, and you will probe polarization rotation, the rotary power of my light-induced chiral state. There's actually two contributions to the response if you pump along the A or the B axis. One will be the generation of a isotropic rotation, which is indicative of plus chiral or minus chiral. And a second one, which will be simply induced by refringence, which has this flower, you'll have sort of this rotation that will, this is what's predicted. So you're supposed to have a background of this plus this spurious signal that has a specific sign theta dependence. This is the data. It looks pretty good. This is you're measuring polarization rotation as a function of time and as a function of incoming polarization angle. You'll see a displacement for pumping one phonon plus these birefringence oscillations. You can filter those out in various ways, and you have rotary induced rotation in that direction. You can pump the other phonon, you have induced rotation in the other direction. And so that's pretty much what we did. Yes?
Does the electronic polarization also get chirality from?
That's a good question. In this specific case, I don't know. Remember, this is a large gap insulator. So there is no free carriers. But a good question is, what if I had a doped system? If I could dope it, would I get interesting? I presume there could be some form of electron phonon coupling that then would give me also the same handedness to the system. Yeah, so in this case, this is only structural chirality. This is the experiment, this is the theory, it was good enough for the referee. What's interesting about this is that if you check the amplitude of the response, this is alpha quartz or beta quartz, I forget. And so the induced chirality is anywhere between 1 to 2 times the chirality of quartz. And if we pump it harder, it would go with the square. So you could get some pretty reasonable induced chirality. I would like to emphasize again how using these compensated structures and uncompensating them, either in ferroelectrics or in, anti-ferroelectrics or in anti-ferromagnets or in anti-ferro, whatever you want, is potentially the way to manipulate these systems without having to deal with awful symmetries. So that brings me to, how much time do I have?
More than 10 minutes.
Okay, I want to tell you about another thing that we're working on. This is a work in progress. I've never given this, so just humor me. Right. So ferroic phases. So this is, big business. We're talking about ferroelectrics, ferromagnets, and they can be classified by the type of symmetry that they break. They either break space inversion symmetry, or they break time reversal symmetry. So this is magnetic and dipolar order. There's also other very beautiful phases. There's this ferrotoroidal state, which is basically having a number of magnetic loops that sort of with the magnetic moments that wind up in a circle. This breaks both time and space inversion symmetry. And then there's this beautiful ferroaxial phase, which breaks neither space nor time reversal symmetry. You should think about this as a set of ferroelectric dipoles that wind around sort of a point, okay? I'll tell you why this is interesting from my standpoint. We have been trying to use light to switch these ferroic properties to generate memories. You want to store one piece of information, say in a ferroelectric state. And we've worked for many years at trying to use the nonlinear phonon Hamiltonian to switch the ferroelectric polarization, say in lithium niobate or some basic ferroelectrics. And we could do this, it kind of worked. This is our early experiments. This is work by Roman Mankowski, where he showed this is some phase-resolved heterodyned second harmonic generation in the ferroelectric, and you could show how you could switch it from positive to negative, and then this thing would switch back, or from negative to positive, and then this thing would switch back. The biggest problem that this type of approach had was that because the ferroelectric polarization has a conjugate field, which is an electric field, it also generates uncompensated charges, which then tend to switch the polarization back. So that's not very good for a memory, because you can switch it, but then you can never get rid of the uncompensated charges, and this thing switches back. Now, what's very nice about the ferroaxial order is that the conjugate field is some sort of curl of E. It's a complicated field that doesn't really have clearly uncompensated dipoles or uncompensated charges. So, and that's why it's also very difficult to manipulate. You can't just apply a field or apply a magnetic field and rotate it. So with these things in mind, we set out to try to find a way, to switch these ferroaxial systems. This is the material of choice. Think of it as this is one of the two domains, that's the other domains. There's a number of octaedra here, and these octaedra are kind of rotating in circles around, and they generate these polarizations that wind together. And there are two ferroaxial states at low temperatures and a paraaxial phase at high temperature. The way you can measure this, again, it doesn't have any linear coupling to electromagnetic fields, but you can probe the appearance of ferroaxial order by looking at dichroism in the second harmonic generation. You can convince yourself that if the ferroelectric dipoles rotate this way or rotate that way, the second harmonic generation generated like so will be different than the second harmonic generation generated with a circular light that rotates in the other way. So, if you do this measure and measure the dichroism, you can measure both the transition at about 190 Kelvin, and you can also measure the domains, plus and minus domains. Right, so this is more complicated. We're working on a figure plan. What this is supposed to tell you is that if you pump the phonons in circles, you will have a force on the ferroaxial mode, which will be proportional to Q cross E, basically Q cross Q dot, which is the same force that generates effective magnetic fields in magnetic systems, or Hall effects in the graphene, but it's basically some rotational motion of the atoms that will displace the ferroaxial mode. So this is a better presentation of this, and this can be done by pumping an EU mode, an odd doubly degenerate mode, which is being driven in circles by using circularly polarized light, which will couple to this A2G mode, which generates this ferroaxial polarization. So we want to use circularly polarized light to displace the ferroaxial polarization. There's two regimes for this. One is at higher temperatures, where there is no ground state ferroaxial polarization, but you can kind of think of this as a paraaxial phase. So as long as you drive it, you could, in principle, polarize your axial state for as long as my drive is on, and then this thing will become non-axial again. And if I go to low temperatures, I will try to switch from phase 1 to phase 2, like in the same vein in what the driven ferroelectric state was. So again, let's start at high temperatures. You start here, there is no axial. You drive the E mode in circles. You couple to the A2G mode, and you displace, by virtue of nonlinear phononics, this ferroaxial coordinate, and you generate the ferroaxial state in one or the other direction, depending on whether you pump right circular or left circular. So the way you do the experiment is by pumping with circularly polarized light and then measuring dichroic second harmonic generation with a circularly polarized probe. And no, if you pump circular right, you generate dichroism up. If you use circular polarized left, you generate. So this is some form of light-induced ferroaxial state or a polarized paraaxial state. Actually, this helped us a lot to think about all our other short-lived states, which are really being driven, and whether we should think about those as some para-something phase that is being polarized by the light field. This effect, this is the TC, where the system acquires spontaneous order.
Sorry.
Yes.
I think you said like it's a centrosymmetric system, and this particular order also doesn't break inversion. So why do we have a second harmonic generation?
The second harmonic, well, I mean, there's not only inversion symmetry breaking that gives you second harmonic generation, okay. Right? So there's a circular.
Right.
Yeah, and in the broken symmetry phase, actually, this is a good point. I don't know if you get, what do you get with a linearly polarized field, right? But presumably, because linearly polarized field is right minus left, you will get something. Actually, you will get something also in, yeah.
Okay, thank you.
So, okay, so this is the simulation, basically some pretty picture of some nonlinear phonon simulation and a simulation of the second harmonic, which pretty much validates what we saw. The most interesting part, however, is the one where we go below TC. We have a system that is either right ferroaxial or left ferroaxial, and you use the same protocol to try to take, this is the equilibrium, double well potential. You basically polarize it and you switch it into this state, or you switch it into that state with right circular or left circular light. Again, because this is not a ferroelectric and doesn't have uncompensated dipoles, in principle you should switch it and it should stay there. And you should use circularly polarized light, and it should come back, and you should do this at terahertz. You should be able to do this. So this is actually very beautiful results from Paul again. This is basically, he's irradiating with many pulses in a kilohertz train, and then he's measuring the integrated second harmonic in a, what is this, right circular, and above a certain fluence, he switches to left circular, and then if he has the other one, he sort of pumps, and then he goes to right circular. But what he showed though, the more interesting part is that if you now take one of these domains and you take one single pulse with right circular polarized, you can take the with something circular polarized, you can take the right domain and make it a left domain. Then you leave your sample there for 10 minutes. You come with the opposite polarization and you switch it back to another non-volatile ultra-fast state. This is a demonstration of this. This is not a particularly good point, but you cool this down. You pump, this is the number of pulses. You pump with the right circular, you switch it in the positive domain, then you come with another pulse, you switch it back, tuck, and all the even pulses will be right circular, all the odd pulses will be left circular. So this presumably can be done at a speed of few with a time spacing of few picoseconds. So it's actually kind of interesting, I think, that this problem of uncompensated charges we were trying to screen in the ferroelectric is not what we should have done. We should look at these ferroaxial stuff. So this brings me to the end. I kind of downloaded on you a lot of information with the characteristic intensity, but I hope you got at least the gist of what I was trying to tell you. The thing that I want to tell you is that I really think we should consider nonlinear phononics in the same category of all these beautiful structural engineering things that people do in equilibrium. Each one of them give you joy in different ways. But this one is really a way to engineer the Hamiltonian in a very precise way. And really, I would like to also add that the frontier of this is the generation of these metastable phases by controlling, it's great to polarize things that then disappear, but you really would like to switch things into metastable states that don't exist in equilibrium or that do, and et cetera, et cetera. So before I free you, I would like to thank all the people that have helped us. So my colleague Paolo Radaelli in Oxford has been a huge inspiration for all of this. He knows symmetry, he teaches it to me. Prabhak is growing samples. Paul Zhang, I hope he graduates soon, otherwise he'll take my job soon. And Michael Fechner is a first principle theorist that allows us to understand which mode couples with which. Michele Buzzi is an experimental hero, is a staff scientist in my department. Emma Amoha is an engineer. Michel First, again, a senior scientist in my group. And this is the new addition to our team, Philip Moll, who is running one of the new directors in Hamburg, and he can prepare samples using various fibbing techniques. And a lot of these experiments, all these experiments would not have been possible without Carsten and Philip preparing samples with us. And everybody else in the group that is really making all of this possible. Thank you for your attention.
For a beautiful talk. For this last part, I didn't quite. What are the specific conditions that you need for your laser, like wavelength and intensity?
Well, in the specific, I forget where the E2U mode is. Let's see, maybe I have. There you go. 24 terahertz.
Okay. 24
terahertz is a high frequency auxiliary mode, and there's two of those. You need two to generate rotational modes. So this is pretty high frequency. It's pretty straightforward. 24 terahertz is about 12 microns.
Okay.
So, yeah.
So this could be really used in the memory. If you want to use it.
I don't know. Ask Jerome. I don't know how much one can make with integrated lasers at 12 microns. Yeah.
You can. Okay.
So maybe if you learn how to focus this properly, maybe this could yeah.
Okay. Hi. Here. I was wondering both at first, is this particular structure, could one also just write that as a helix? And second, what is the exact mechanism how your differently circularly polarized light actually couples?
Good point. Okay. This is not a helix, this is an axial field, so it's basically a two-dimensional. Come again, sorry? Sorry. You can think of this as layers, but unlike chirality, which needs a third dimension, this is really the axial field is just a two-dimensional.
So what is your error in the middle then?
That is the moment. So I have defined,
So
I have defined a moment that is proportional to somehow the curl of V, or the curl of the polarization.
Okay, yeah, I misunderstood.
Right. Sorry, this was supposed to be the conjugate quantity.
Yeah. And I also asked, what is exactly the mechanism how your circular field?
This is actually, okay. This is what we're writing the figure for the paper. We're trying to explain basically because the driving field is a crossing between the curl between Q and the electric field. All right. How did this work? You can convince yourself that as the cross product of Q and E is rotating around over a cycle, it exerts a force that is always in the same direction along the ferroaxial field. I don't know, if you reviewed this, would you understand it? Yes. Okay, that's what we're trying to. Yeah.
All right, Daniele, then Dennis.
Yeah. Also a question on the same line, that, so is this nonlinear phononics in the sense that everything seems linearly coupled?
I've tried and failed to convince Paul to call this Q cross Q dot, but he is adamant that it should be Q cross E. In other words,
yeah, because it all
whether
seems linear.
E is important or Q dot, which is proportional to E, is important, I don't know. But, you know, I can't control the man. He wants to put E in there. So, what's that?
He wants to really take it.
That's right, that's right. So, but it's basically the same thing. I mean, you can think of this as Q cross Q dot. So in a sense, it is non-linear. Remember, all circular phonons, they're all Q cross Q dot, right? It's, yeah.
So whenever you have this kind of a photo-induced phase transition, some kind of a metastable phase, right? There first you ask, is there some critical excitation which I have to make in over total? But it's not, I'm not over yet. And the second problem is, if you hit it too much, you're gonna basically maybe destroy this landscape. So do you see both of the limits? So
we didn't pump that hard.
Usually, the first one,
usually experimental protocol, you push it until it works and then you stop measuring, right? It's, no, I don't think we'd have enough light.
But my question is, is there for a single excitation?
Yes.
Do you get for a single excitation? Do you get can you already switch, or do you need many pulses?
Now these are single shot experiments.
This is a single shot.
These are single shot, right? Even odd pulses where you switch it left and right.
And this has a critical excitation.
Well, basically we took what we knew from multi-shot. This was the pump fluence per pulse in millijoules per square centimeter. And then we built a fast shutter so that we could have these pulses. So we've used, so the answer is yes. If you pump too little, then this thing doesn't switch. I mean, again, remember, what you're trying to do is to take this double well potential and tilt it just enough so that this thing will roll over, at least at a very qualitative level. Yeah.
Andrea, I've got a question too. Very nice talk, by the way. So if you take the system and cool it down to low enough temperature, will it become more and more difficult for you to tip such that it rolls over? Right,
photosusceptibility we haven't characterized yet. We're trying to look at some Curie, because we're thinking about this para-axial, ferroaxial, we're trying to find some dynamically Curie-Weiss-like divergence. We're in the process of doing that. I don't have a very... But potentially, what I'm expecting is that the closer you are to the transition, the softer the system will become, and then this will potentially saturate somewhere below TC. Yeah.
Finally done. So I want to circle back to Michael's question, because you put a challenge in the last slide, like saving planet, right?
Yeah, you're right.
So power is important, right? So how should I think about these transitions? Like, how do they scale with area? Should I think of them as like domains that we're inverting, or no? The whole macroscopic system is going through some transition.
Right.
Like,
okay.
Can I think of like maybe you say that you're not the best person to answer this, but are there like toy models that one can write to imagine that you have the best material and engineering, etc. What are the fundamental limits of how many photons I need to do this kind of stuff?
I see.
In other words, like I look at the depth of these potentials, these are phenomenological curves, right?
I mean, this is really a Mickey Mouse classical model, right? So this doesn't inform
you've thought about
very much. So I don't really know how to. Yeah, I understand what you're saying. I mean, is there sort of a how does that threshold work? How does it and is it sort of a space?
Exactly.
I mean, the domains form naturally because you have two types of polarizations, and then you in equilibrium. I think we understand that in dynamic. I mean, I don't know what to say. I'm not sure this specific problem is the most interesting place to be asking.
No, but generally, most of the things that you show in your talks, like, have these double wells.
Yeah.
And there is a depth to that.
Yes.
And
that's an equilibrium, right? That's the equilibrium.
Like how many photons I need to climb up that hill?
You're not climbing, remember, you're reshaping. This terms comes into the Hamiltonian.
Yeah, that's what I mean, yeah.
And what it's doing is it's basically generating a field that tilts your double well potential. So at zero order, the number of photons will be determined by this number beta here. I think there's a lot of mechanistics that we need to work on before we can ask these questions. How narrow of a pulse, how long of a pulse, what optimizes.
Thank you.
Yeah.
Thanks.
Yes, so a question on this BPO4 part. Can you write a spin model, or that could this chirality, like phone chirality, bring some chiral time-dependent interactions for the...
Right, so Atash was asking this. There's no charges, right? This is an insulator with a 3D gap at least.
So it's,
yeah.
You cannot even
That's right. I mean, maybe there's something equivalent. I don't know how many of these antiferrochirals there are, actually. Maybe that's, we haven't gotten that far yet, but maybe one should think about antiferrochirals which can be doped as a means to polarize both the structure and with that the electronic wave functions. Yeah.
And the ingredient is to have both chiralities kind of in.
Well, one way to do it easily without having to go crazy is to have already the two hands in the structure, right? Then there's a natural way too, by phononics, to make one bigger than the other. Yeah.
Yeah, so this very beautiful light-induced chirality where the B mode, what frequency is that? We're very
the low frequency B mode, you mean?
Oh, yes.
I mean, it's a soft mode.
No, it's not soft, for the BPO work. Yeah. So
BPO4?
Yeah, BPO4, yeah. Because that's, if we're driving resonantly, so usually for this,
no, but this is an even mode. You can't drive with light, right?
That's right, yeah. But then if we drive a pulse, you would expect, in the first work,
sorry, are we talking about chirality or are we talking
the chirality.
Oh, chirality.
Yeah. So in that one, yeah, so are we driving an oscillating B mode, or basically we're just pushing slightly towards the...
In the specific case here, this is being pushed quasi-adiabatically.
Yeah, so that's because the B mode is very off-resonant.
Is fast enough compared to the... So you will respond fast enough compared to the envelope of the drive. There's probably other regimes where you can impulsively kick it.
I see. Okay, got it.
Yeah.
Thank you.
So I don't want to dwell too much on this, but following up on this, so if the valence electrons were to sort of experience the chirality, but the conduction band not, or vice versa, then the electronic polarization would, even in the absence of carriers, isn't it? I mean, you virtually excite carriers into bands, right? So that's how I think about electronic polarization.
So what you're saying, I mean, there should be, can I translate this? Yeah. You're saying, is there going to be a displacement field somehow that retains this? Maybe, sure. I haven't thought about it very deeply, but that's an interesting, yeah.
Okay, just adding to attach question. I think you have an insulator, you have all the symmetry broken, and then you can have these shift currents, which is equivalent to the polarization that attach is having. And that is going to be a permanent effect that will induce this electronic contribution to the effect.
I see.
And I think you don't need to have doping.
The field valence bands will know that the system is chiral in some way. Yeah. I see. Is it interesting? Yeah. No, that's great. Sure.
Sebastian. Yeah. I mean, it's very nice how you can really drive these systems on the microscopic level. I mean, if you didn't know about that and you would just ask about some observables on the macroscopic scale, could you also see some observables that you cannot have at equilibrium? For example, I mean, something like odd or non-reciprocal transport, or, I mean, it reminds me a bit of what people are discussing, so odd viscosity, odd elasticity in systems of basically the hydrodynamics of complex lattice vibrations. If you push them out of equilibrium, you can have forms of transport that you don't have.
I mean, is this a general question about all these driven systems?
A general one, yeah, about, well, I mean, maybe specific to these big coupled phonon systems, yeah.
And we're not talking about something that happens already spontaneously at low temperature happening at higher temperatures, because there I have an answer.
Yeah, I mean, if you can basically prove just based on observables that your system is
well, I mean, look, strontium titanate is a system that when it's not strained, it's not ferroelectric. And when you do these kind of excitations, I mean, we've heard yesterday, you can polarize it. That's an example of something that doesn't happen in equilibrium, right? BPO4 is not chiral, although we're cheating because it is chiral, but and it can be made chiral. Then we're negotiating whether something interesting is happening or something boring is happening. That is
right. But this ferroelectric order, you could also have it in another equilibrium system.
Oh, I see. You want to see something. You want to see something that humans have never seen. And, well, yeah, maybe I don't know.
I mean,
in
active matter, people are looking at.
Yeah, I don't know of any genuinely new physical phenomenon that can be, but it would be great. You know.
One more question.
Yes.
Hi, Andrea. What are the prospects for switching toroidal orders or even multipolar orders?
Yeah, so I don't have any, I mean, we're working on this, trying to find an interesting angle. There's probably, the question is, what do we want to do with toroidal orders? Do you want something that is not toroidally ordered, or you want to switch direction of it?
Well,
I don't have a well-argued answer. We're sort of thinking about this.
I can talk to you offline.
All right, let's thank Andrea again.